Course 2, Lesson 4 is going to focus on number lines and sequences. So a number line can be used to help us arrange numbers in order. Each number corresponds to a unique point on the number line. The 0 point of a number line is called the origin. So as you can see here, the 0 point is the origin. The numbers to the right of the origin are positive numbers, and they are all greater than 0. Every positive number has an opposite that is the same distance to the left of the origin. So these numbers to the left of the origin are called negative numbers. So the negative numbers are all less than 0, and 0 is neither positive nor negative. So on this number line, the tick marks that you can see here indicate the location of integers. So integers include all of the counting numbers as well as their opposites, their negatives, and the number 0. However, integers do not include fractions or any other numbers that are between these consecutive tick marks on the number line. So, as we move to the right on a number line, the numbers become greater and greater. However, when we move to the left on a number line, the numbers become less and less. So a number is greater than another number if it is farther to the right on a number line. So we can compare two numbers by determining whether one is greater than the other or whether the numbers are equal. So what you'll do is you'll place what's called a comparison symbol between two numbers to show the comparison. So the comparison symbols are the equal sign, which we know what the equal sign looks like, and the greater than, less than symbols, which look like this or this. So we write the greater than and less than symbols so that the smaller end, which is the point, points to the number that is less. Below, we will see three different comparisons. So we have a -5 and 4. So we know that -5 is less than 4, so we will draw the less than symbol. So when you read it from left to right, it will read as -5 is less than 4. And then the point here of this comparison symbol is also pointing to the number that is less. The next one we have 3 plus 2, and we have 5. So when you have this, you'll just want to solve for 3 plus 2, which will give you 5. So that gives you the answer that these are equal. And then the next one is 5 and -6. So we know that 5 is greater than -6. So we will draw this symbol. And we can see that the point is pointing to the number that is less than. So for example 1, we want to arrange these numbers in order from least to greatest. So we have 0, 1, and -2. So you can arrange these numbers in the order of which they appear on a number line. So when you do that, you will see that the smallest number is -2. The next number would be 0, and then the greatest number would be 1. But you probably don't need to draw a number line because you might be able to easily identify which is least to greatest by just looking at them. For example 2, we want to rewrite the expression below by replacing the circle with the correct comparison symbol. Then use the words to write the comparison. So we have a -5, then we have our circle, and then we have 3. So by looking at this, we know that -5 is less than 3. So we will write the less than symbol. And again, this point here in the comparison symbol is pointing to -5. The lower number. So if we get rid of the circle, it looks like this. And then to write it in words, we would just write -5 is less than 3. Okay, so we can also use the number line to help us add and subtract. We will use arrows to show addition and subtraction. So to add, we would let the arrow point to the right, and then to subtract, we would let the arrow point to the left. So if we look at example 3, we want to show this addition problem on a number line. So we have 3 plus 2. So we will draw our number line. We'll draw the origin 0. We'll draw 1, 2, 3, 4, 5. And then the opposites, -1, -2, -3, -4, and -5. Okay, so what you're going to do is you're going to start at your origin. So you're going to start at 0. And then what you're going to do is you're going to draw an arrow 3 units long that points to the right. So we'll move up a little, and then we'll go 1, 2, 3. Okay? And then from this arrowhead, you're going to draw another arrow that is 2 units long that points to the right. So we'll go up again, and then we'll go 1, 2. So then if you just go back down, you'll see what number it matches up with. So then this gives you the answer of 3 plus 2 equals 5. For example 4, we need to show this subtraction problem on a number line. So we have 5 minus 3. So what we're going to do, we're again going to start at the origin here at 0. And since we have a positive 5, we are going to draw an arrow 5 units long that points to the right. So you go up, you go 1, 2, 3, 4, and I need to make my number line longer, and 5. So then you need to draw a second arrow 3 units long that is going to point to the left, and we are doing this because we are subtracting 3 now. So we'll go up, we'll go 1, 2, and 3. So if we go down, your answer will be 2. So then this gives us our answer as 5 minus 3 equals 2. So for example 5, we need to show this subtraction problem on a number line as well. So we have 3 minus 5. So let's take our number line. We'll do 0, 1, 2, 3, 4. Let's draw our negative numbers. And then what we are going to do, we will start by drawing an arrow 3 units long to the right. So we'll go up, we'll go 1, 2, 3. But now since we are subtracting, we need to draw another arrow 5 units long, but it's going to be to the left since we're subtracting. So we'll go up again, we'll go 1, 2, 3, 4, and 5. So if we come all the way down, we see that our answer is now -2. So this shows that 3 minus 5 equals -2. So if we take a look at examples 4 and examples 5, these show graphically that subtraction is not commutative. So we know that the order of the numbers do affect the outcome in subtraction. However, we do also notice that reversing the order of subtraction results in opposite differences. So we found that 5 minus 3 equals 2, and then when we did 3 minus 5, our answer was -2. So we can use this characteristic of subtraction to help us with subtraction problems like the next example we'll see. So for example 6, we want to simplify 376 minus 840. So immediately looking at this problem, we know that our result is going to be negative. However, we can reverse the order of the numbers to form the subtraction. So you can switch it to be 840 minus 376. So you can set that up. And once you do that math, your answer will be 464. So we know that the answer to the original problem is the opposite of 464. So our answer will now be negative 464. Now we will move on to sequences. So a sequence is an ordered list of terms that follows a certain rule or a certain pattern. So a list of the whole numbers is an example of a sequence. So you can see the whole numbers here. We have 0, 1, 2, 3, 4. This is a sequence. If we would want to list the even or odd whole numbers, we could write the following sequences. So we have the even numbers, 0, 2, 4, 6, 8, and then we have the odd numbers, 1, 3, 5, 7, 9. So these sequences are what we call arithmetic sequences because the same number is added to each term in order to find the next term. Thus, the numbers in the sequence are equally spaced on a number line. So we can see the number line here. So we have our even numbers, 0, 2, 4, 6, 8, 10. And then we have our odd numbers, 1, 3, 5, 7, 9. So they are all equally spaced on their number lines. So if we look at a different sequence, we have 1, 2, 4, 8, 16, and so on. This sequence is what we would call a geometric sequence because each term is multiplied by the same number to find the next term. So terms in a geometric sequence are not equally spaced on a number line. So if we draw this out quickly, we have 0, we have 1, 2, so these are both our numbers. We have 3, 4 is our number, 5, 6, 7. We have 8 is our next number. So we can see that they are not equally spaced on the number line like our arithmetic sequences were. So to continue in a sequence, we want to study the sequence to understand its pattern or the rule, and then we would apply the rule to find additional terms in the sequence. So for example 7, the first 4 terms of the sequence are shown below. We need to find the next 3 terms in the sequence. So we have 1, 4, 9, 16, and so on. So when we first look at this, we can see that this sequence is neither arithmetic nor geometric. We can see that the terms are increasing in size by a larger amount as we move to the right in the sequence. So in order to find these next 3 terms, we have to figure out the pattern or the rule that this sequence is following. So we need to look at how 1 gets to 4. How does 4 get to 9? How does 9 get to 16, and so on. So we can see that if we take 1, we add 3, and you get to 4. You take 4, and you add 5, you get to 9. You take 9, you add 7, we get to 16, okay? So this itself forms a sequence that we may recognize, right? We're seeing odd numbers, the odd number sequence that we had listed before. So all we're going to do is continue the sequence by adding larger odd numbers. So to get to our next number, you're going to take 16 and you're going to add 9, and that will give us 25. To get to our next number, you're going to take 25 and you're going to add 11, and you're going to get 36. And then to get to our next number, you'll take 36 and you're going to add 13, and you'll get 49. Okay? So we find that our next 3 numbers in this sequence are 25, 36, and 49. There's also another solution to this problem. So we can recognize that this sequence is a list of perfect squares. So when we multiply a counting number by itself, the product is a perfect square. So if we see this, we see that 1 times 1 equals 1. We see that 2 times 2 equals 4. We see that 3 times 3 equals 9. Then we'll see that 4 times 4 equals 16. And then we have our 1, we have our 4, we have our 9 and we have our 16, and these are all the digits that we have. So for continuing this pattern, you can continue doing 5 times 5, which equals 25. You can do 6 times 6, which equals 36. And then you can also do 7 times 7, which equals 49. And we get our next 3 digits of the sequence. So the rule of a sequence might be expressed as a formula. So a formula for the sequence of a perfect square would be k equals n times n. So this variable n here represents the position of the term. So it could be the first one, the second one, or the third one. And then k represents the value of the term. So this could have been 1, 4, 9, as we saw in our previous example. So to find the 8th term of the sequence from the previous example, we would write 8 in place of n and find k. So we go 8 times 8, and then we solve this, we get 64. So this tells us that since 8 times 8 is 64, the 8th term is 64. All right, and for our last example, example 8, the rule of a certain sequence is k equals 2n. So we have to find the first 4 terms of the sequence. So in order to figure this out, we need to substitute 1, 2, 3, and 4 for n in order to find the first terms. So for the first term, you are going to write our rule out. So k equals 2, and then in place of n, you will write 1. So once we solve this, k equals 2. For the second term, we're going to do the same thing. We will write out our rule, k equals 2, fill in a 2 here, and this equals 4. For our third term, we are going to write k equals 2, and then we'll fill in a 3, equals 6. And for our fourth term, I'm running out of room. Fourth term, we will write k equals 2 times 4, which is 8. So we know that the first 4 terms of the sequence are 2, 4, 6, and 8. And we plugged in 1, 2, 3, and 4 for n here because if we remember, the variable n represents the position of the term. So when we're looking for the first term, it's in the first position, right? So you'll plug in a 1. Same for the second term, it's in the second position, so we'll plug in a 2. And so on for the third and the fourth term as well.